Welcome back, students. In this lecture we will see how to draw inference line diagram for bending moments at a point in a indeterminate beam. Okay, so from previous lecture we already found out that we can employ the Moeller-Breslau principle to draw the ILD for bending moment here also, even if the beam is indeterminate, right? So let's say that we have to draw the inference line diagram for bending moment at E. So in order to do that, what we do is at E we will place a internal hinge. So this internal hinge is such that it can transfer shear forces, but it cannot transfer any moment. And then at this internal hinge, all we do is we will apply a positive couple moment, a unit positive couple moment. So what happens when the moment is applied, the beam will deflect. Okay, and the final deflect shape of this particular beam will be nothing but the shape of the ILD. Okay, and from the proper analysis using force methods and Maxwell's theorem of reciprocal displacement, we can find that the ILD for bending moment at E is nothing but the deflected shape, the deflection at each point this particular beam divided by alpha EE, where alpha EE is nothing but the angular displacement at the point E. Okay, so this also verifies the Moeller-Breslau theorem as well, right? So let's see an example. So just like we did for the shear force, we have the same problem here, but instead we have to find the bending moment at T, ILD for bending moment at T. Okay, so without any delay, let's get started with the problem. So what we do initially is at the point D we'll insert a hinge. So the point D becomes a hinge and the beam gets separated into two parts, which is AD and DVC, right? And at the point of D we'll apply a unit positive couple, so 1 kilofit each on either side of D will apply, right? So next step we have to do is we have to find out the equilibrium of this particular real beam, which is by equilibrium method. So by equilibrium equations you have to find out the reactions at A, B and C. So if we take this part, like the beam AD, let's say that there is another, in order to balance this, there is a force applied. So when this 1 kilonewton force is applied at a distance of 9, okay, this can be said that at A there is a force of about 1 by 9, which is nothing but 0.111. So if there is an upward force, in order to balance that, the shear at D will be downward and the value will be 0.11 k, right? Since this is a hinge, you can say that if there is a shear force acting downward, which is 0.11, there will be a shear force acting upward as well, right? This will also be 0.111, which is nothing but 1 by 9, right? So we got already the reaction at A, which is RA is upward with 0.11 k. Now you have to take the equilibrium of the beam in the right hand side of the hinge, right, which is nothing but DBC. So when you have to take the equilibrium of this, you have to find out the reaction RC RB, right? So all you do is take moment about this P as 0, which means that there is a moment of clockwise moment of 1k plus another clockwise moment caused by 0.11 into 9, which is nothing but again 1k. So 1k plus 1k, there is a total clockwise moment of 2k, and it is to be counterbalanced by a moment is equal to 18 into RC, which means that RC is equal to 2 by 18, which is again 1 by 9, which is nothing but 0.11 k. If we take sigma Fy equal to 0, you can say that RC plus RB is equal to RC plus RB plus 0.11 equal to 0, which means that you can find that RB is equal to 0.11 k plus 0.11 k, which is nothing but 0.22 k. So now that you have find out the reactions of the real beam, you can also find out the bending moment of the real beam. So if you try to plot the bending moment for this real beam using the given equation react obtained reactions, you can find that the bending moment of this real beam is going to be something like triangle. Okay, it's going to be something like a triangle. The maximum ordinate will be at B, and it is equal to 2 by EI, which is nothing but 0.11 into 18, right? So this will be the bending moment, which is again positive bending moment, right? So in order to find out the ILD, all you do is you have to apply a unit load, unit couple moment at D. So if you apply unit couple moment, the deflection pattern will be something like this. We already know. So in order to find out this deflection values at each point, you can employ the conjugate beam method. So you already have a real beam here with pin support as A, B and C and a hinge at D. So the conjugate beam of that will be the internal hinge will become an internal roller, and the internal roller will become a hinge in the conjugate beam. Okay, the other pin joints which are outside will remain as the same, right? So this conjugate beam has to be now subjected with the M by A diagram of the, oh, sorry, here EI is not there, sorry. So this has to be loaded with the M by A diagram, so which is nothing but the same triangle divided by EI, which makes it is 2 by EI, right? Now you have to find, all you have to find is the reaction in this conjugate beam, and once the reaction is obtained in this conjugate beam, in order to know the deflection at each point, all you need to do is you have to find out the bending moment at those points, right? So if you want to know the deflection at D, you have to find out the bending moment in the conjugate beam at D. If you want to find out the deflection at E, just this, you have to find out the bending moment at E in the conjugate beam, right? So let's find out the consider the equilibrium of this conjugate beam. So let's divide the beam at this particular hinge so that there is two spans, which is BC and BDA, right? So let's start with the right hand section. So the loading in the right hand section is like a right angle triangle which vertical as 2 by EI and base as 18, which means that the total load acting will be area of the triangle, which is nothing but half into 2 by EI into 18, which means the total load to be 18 by EI, right? So this 18 by EI will be acting at a distance of base by 3, which is 18 by 3, which is 6 feet. Okay, the moment that hinge is to be 0, so 18 into 6 is equal to RC dash into 18, which means that 8 RC dash is going to be 6 by EI acting downward. The total upward force is 18, which means that the shear at this point is going to be again 18 minus 6 by EI, which is nothing but 12 by EI, right? So if there is a downward shear on the right hand side, there should be an upward shear on the left hand side of B having the same value 12 by EI. Okay, also we had the net moment, sorry, the net load on the span ADB will also be 18 by EI upward acting at a distance of 6 feet from the right angle, right? Now if you have to find out the reaction at A, you can say that 18 by EI will, you can take moment about D dash as 0, which is a support. So you can take moment about A dash equal to 0, which is a roller support. So when you do that, you can say that RD dash into 9 feet, RD dash into 9 plus 18 into 6 and 9. 9 plus 6, which is 15, plus 12 by A into 18 equal to 0, which means that you can find that RD dash is downward 48 by EI. The net upward force is 18 by EI plus 12 by EI, which is 30. So the remaining force is from RA dash. So 18 plus this shear force, which is 12 by EI plus 18 by EI, 30 by EI minus 48 by EI, which is nothing but 18 by EI, right? So we got RA dash also. Okay, you have to find out the deflection at each point in the real beam. So the deflection pattern will look something like this. So we have to find out each deflection. Let's say deflection at A, D, B, etc. So at A, if you want to find out deflection, you have to find out the bending moment at D in the conjugate beam. If at E you have to find out the deflection, you have to find out the bending moment at E dash in the conjugate. So let's get started. So initially you can see that from the deflection pattern only, the deflection at A, deflection at B and deflection at C is going to be 0, right? And this was our conjugate beam, right? So next is we have to find out the deflection at D, which means that it is nothing but you have to find out the bending moment at D in the conjugate beam. So you can take this portion outside, the left portion of D outside, you get the diagram something like this. So 18 by EI into 9, so empty dash, which is nothing but delta at D, is equal to going to be 18 by EI into 9 feet plus 4.5 into by EI into 3 feet, which is nothing but 175.5. This 4.5 by EI is nothing but the area of this triangle, which is half into 1 by EI into 9, right? The next thing, if you want, you have to find out is delta E, which is nothing but bending moment at E. So you can find it as, if you take the right hand portion of this E, so you can say that it is going to be half into area of the triangle, half into 1 by EI into 9, which is going to be 4.5 by EI, which is acting at a distance of 3 feet. So this is clockwise, so when it's so this is anti-clockwise, on the right hand side is positive, minus 6 by EI into 9. This total length is 9. So if you do that, you get the deflection at E is equal to 40.5 minus 40.5 by EI, right? So now if you want to find out the, now you have already had the deflection at each point. Now you have to find out the bending coordinates of the ILD for bending moment. All you need to find is divide the deflection at each point by the angular displacement at T alpha, that is nothing but theta at T, which is going to be shear force at D. So shear force at D is nothing but the reaction at D, which was nothing but 48 by VI. So we already have the deflection at different points A, D, B, E, C. So now if we divide this values by 48 by EI, you will get the ILD for ordinates of ILD for bending moment at D, right? So 48 by 175.5 by 48 is going to be something like 3.6. This by 48 is going to be something like 0.4. Now you have the values of ILD, ordinates of ILD. You can now just plot that and show that as an ILD diagram, right? So that's it for today's lecture. Thank you.